Is there life on Mars? Has there ever been? These questions have inspired science and science fiction alike. But a mission, led by the European and Russian space agencies, might finally reveal what really lies beneath the surface of Red Planet. We have been sending missions to Mars since the 1960s to find out what, if anything, could survive there. In 1976, the Viking 1 lander made history as the spacecraft to successfully land on another planet. 20 years later, Mars Pathfinder was better able to explore the surface, as the first mission to use a rover alongside a lander. More recently, the twin rovers, Spirit and Opportunity, have proved that the surface may once have been covered in oceans and lakes. And, in 2018, the Curiosity rover found evidence of organic molecules, the raw building blocks for life. However, no signs of life have yet been confirmed, but an upcoming mission could change that. This is the ExoMars rover. It will be the most advanced rover sent to Mars. It's being developed just north of London by Airbus in a purpose-built Mars yard. The Mars yard is a simulated Martian environment. It has the right sands and rock types that we expect to encounter on Mars, which we then use to develop our prototype rovers. We're very much in the age of the rover. We don't really now on Mars is most interesting to take samples and look for signs of life. So we want to use rovers rather than landers to cover as much distance as we can and try lots of different scientific sites. We design a rover to be able to drive long distances on Mars. There are two main challenges that we have to design around. The first of these is the thermal environment. The temperature range on Mars can go between 10 degrees in the day to 130 degrees at night. The electronics that sit inside our rover and control everything.
They don't like it at the very low temperature, and we have to design an environment on board that isolates the electronics from these extremes of temperature. The second is dust, particularly for a solar-powered mission like ours. Dust storms on Mars tend to be peaking around the Martian winter, and so the simple way to design the mission around them is to land just after the Martian winter in the Martian springtime. They will be something we'll have to deal with eventually, but the idea is that we've achieved all our scientific goals by then. The navigation of the rover and the way it's able to move around is really important, because the time delay between Earth and Mars can be as bad as 20 minutes. So it's either really inefficient to drive it by remote control, or it's actually dangerous. So instead we've designed our rover to be as autonomous as we possibly, to the point where all it needs is the target we want it to reach. We tell it nothing about the terrain, we tell it nothing about the best route to take. Everything else is done on board. The navigation cameras at the top of the mast, they see in 3D, and that allows the rover to determine where the rocks and the slopes are in front of it. If any of those rocks are too big or the slope is too steep, that area will be marked as forbidden and the rover will not go anywhere near it.
There's also quite an interesting feature in the locomotion system called trajectory control, if we start to get disturbed from the path we're trying to follow.
Because of the nature of the terrain, the system realizes that is happening and will bring us back onto the path we're trying to follow. That's more efficient, but it's also safer for the rover as well. We have a really flexible locomotion system in that we can actually steer and drive all 6 wheels at the same time.
This allows us to follow a curve, crab sideways, spin on the spot, and we can actually do a combination of these geometries to achieve different effects whilst we're driving.
That's something no other rover has been able to do to date. To know where to go, the rover will need a pair of eyes. Luckily, the Mullard Space Science Laboratory is up to the challenge. We're working on the ExoMars Pancam, the panoramic camera system, so this is the scientific eyes of the rover.
This will actually be able to do some geology and some atmospheric science. It uses a combination of cameras to be able to do that.
Yes, so this the Pancam optical bench, so that's the thing that houses all the camera system, so it has two apertures here, each of those for the two wide-angle cameras, and is the high-resolution camera aperture. And so Pancam is inside this optical bench and the real thing is sealed on Mars.
The rover is going to be drilling underneath the surface of Mars for the first time to look for signs of life, but to do that you've got to decide where to drill, so we have context instruments.
So Pancam is the most important of those, but there are several others. As well as Pancam, there's the infrared spectrometer, there's close-up imager, there's a subsurface sounding radar, there's neutron detector, and there is also a little camera inside the drill tip. The ExoMars rover will be the first mission to drill deep down into the Martian surface. It will drill 2 meters down, to where scientists believe there may be a layer of permafrost. This is where they'll look evidence of life in the past or even life today. What we do is get the sample from underneath the surface, bring it up to the rover and put it inside what's called the analytical drawer. And then there are 3 more instruments inside of there which will analyze the sample. So that combination, the context instruments tell you where to drill. Then once you've drilled, we look at analyzing the sample. We're not expecting to find things like dinosaur bones, for example. Potentially going to be things like traces of fossilized bacteria. All the instruments, robotics, and computing power mean nothing if the rover doesn't land in the right place. So experts at the Natural History Museum have joined an international effort to figure it out. Choosing where to land on Mars is actually quite a challenge because we want to land on the teally old parts of Mars where we think we stand the best chance of finding traces of past life. But these regions also tend to be pretty high, so there's less atmosphere to slow a rover down as we descend towards the surface of Mars. So it's really about finding a balance between somewhere that's relatively low and somewhere that's relatively old. So we're landing in this region northwest Arabia Terra, here, because it's actually quite near the hemispheric divide on Mars where the southern highlands, the old part of Mars, borders the northern lowland, the young part of Mars. So this region here has the advantage of being relatively low down, so there's enough atmosphere, but is also relatively old. Margin for error in where we're actually going to land, it's about 100 kilometers or so. So we need to be very sure that the entire area across these 2 sites, across the entire landing area, is safe for the rover to land and safe for it to explore, but also that there's going to be good science to do wherever we land within the sites. The thing I'm most worried about, I guess, is the landing. The time delay is as much as 7 minutes at that point.
It tends to get referred to as the 7 minutes of terror, and thus the landing system has to be able to land the rover safely, all without any interaction from Earth.
Earth will only find out if it's landed 7 minutes after it either has or hasn't, on the surface, so that will be quite a nervous time. The landing sites are selected in sort of a balancing act to make sure that the rover can deal with the environment that will encounter once it lands on Mars. Inevitably, most of the scientifically interesting sites are the hardest to get to. The 2 sites where the rover could potentially land are called Morth Vallis and Oxyoplanum. And both sites are covered in clay minerals. Clay minerals are important because we think they form in water on the Earth. So we think that 4 billion years ago these clay minerals at the 2 sites formed somehow in liquid water, and we think they would potentially be good at preserving signs of life, so organics. To help inform the ExoMars mission, scientists have been working with some pieces of Mars that we have right here, on Earth. So the museum has one of the best collections of Martian meteorites in the world because it's quite a diverse collection. The cream of the meteorite collection for Martian meteorites is this one here called Nakla, which fell about 100 years ago, in Egypt. In the 1980s, researchers at the museum found that it actually contained traces of water, and this was the first evidence that the planet Mars actually has water on it. It's one thing to find water on Mars, but life? One of the really big questions is whether there's life on Mars, because once we did think it was much warmer and wetter, and so it might have been habitable. In 1996, a group of researchers published evidence for fossilized bacterial type life. They found these little fossil morphologies in a meteorite called Allen Hills 84001. And we now think these little wormy things they found were probably not fossilized Martian life, but it's really invigorated the debate. and absolutely one day we might find that evidence that we've been looking for. That was life on Mars. Other rovers started off looking for water and following the water, now looking at habitability, but we're going right to the heart of the question of was there life there? My feeling is that Mars was formed around the same time as the Earth in a similar part of the solar system, where water can exist as a liquid, and if our assumptions about what life needs are correct, then in theory we should find it next door. I think it'll be bacterial level of life. It's the most hardy form of life we have on Earth, so if we do find it, it'll be that, but I'm fairly confident we will find we're looking for. Yes. Mars probably had the conditions for life 4 billion years ago, so whether or not life evolved there is an interesting question. 2 planets within a solar system both hosting life is quite a good sign for perhaps life elsewhere in the universe. Ultimately, that's what's most exciting about the ExoMars mission. If we find life on Mars, there's no limit to where else in the universe life has found a way.